Hello students, welcome back to the lecture series of rotational dynamics. Today we are going to start with a question which is given on the screen. So we have been given a rod and the length of the rod is L and its mass is M. And we have been told that there is an axis, the dotted red axis. It passes through the center of mass of the rod. And the moment of inertia of the rod about this axis is ml square by 12 as shown in the figure. What they're asking us to calculate is the moment of inertia about a new axis, the black dotted axis, and this new axis is passing through one end of the rod. So we have been given moment of inertia about an axis passing through the center of mass, and we have been asked to find moment of inertia about a new axis passing through the end of the rod. And these two axes, it has been given that they both are parallel. So to find the answer to this question, let's first study the topic of today's lecture and then solve this question. So to solve this question, we need to understand a topic called as parallel axis theorem. Parallel axis theorem. And once we understand this theorem, we will be in a position to answer this question, which will be done at the end of the lecture. So let's start with a statement of the parallel axis theorem. I'll read it out. So if the moment of inertia of an object about an axis passing through center of mass is given as IC, then moment of inertia about an axis parallel to the axis through center of mass is given by I is equal to IC plus MH square. And the H is nothing but the distance between the two axes, and M is nothing but the mass of the body. So this is what parallel axis theorem states. I is equal to IC plus MH square. What we are going to do is we are going to derive this formula today. I is equal to IC plus MH square. But before starting with the derivation, we need to understand the conditions that need to be satisfied so that we can use parallel axis theorem. The first condition that needs to be satisfied is we should have a body and there should be two parallel axes mentioned. And out of those two parallel axes, one of the axes must pass through center of mass. So if these two conditions are satisfied, then we are in a position to calculate or to use, the parallel axis theorem. Okay, so let's start the derivation. Now I have some points over here to start the derivation. So what we are doing is that we are considering a point D. So we are considering a point D, and at point D, we are placing a small mass dm. Now, this dm is a point mass. So we can write down the moment of inertia of this small point particle mass dm about an axis passing through center of mass, which is this. And it can be written as dic is equal to dc square into dm. dc is the distance between the axis of rotation that is passing through center of mass and the point particle dm. Therefore, the total moment of inertia about the center of mass, about an axis passing through the center of mass, will be integral dc square into dm. We add the small dics, that is integrate, to get the total moment of inertia ic about an axis passing through center of mass. C is nothing but center of mass. Similarly, we have another axis which is passing through point O, and the moment of inertia about that axis passing through O for the point particle dm can be written as IO is equal to integral dO square into dm. Now this IO is what we have to find out. This IO is what we have to find out. Now that IO is equal to, now this dO can be written as dn square plus no square. dn square plus no square, because we have a right angle triangle dno. So integral dn square plus no square into dm, which is equal to integral. Let's keep the dn square as it is. But if you look at the diagram, nc can be written as, no can be written as nc plus co. So no is written as nc plus co whole square and bracket into dm. Now let's open the brackets. So we have integral dn square plus nc square plus twice nc co plus co square whole into dm. Now let's open the brackets and give multiply dm to all the quantities inside the bracket. Before doing that, let's specify the distance, which I forgot to, between the axis, and let's specify the distance as h in the diagram. So in the place of, before getting the dm's with all the terms, we will first substitute h in the place of co. So we can write down integral dn square plus nc square plus 2nc co plus co square. Sorry, in the place of co, we have to write h. Yes, h plus h square whole into dm. Now, if you look at the diagram, dn square plus nc square can be written as dc square. So, integral dc square plus 2nch plus h square dm. So this is what we have. Now let's open the bracket and multiply the dm's with all the terms inside the bracket. Okay, so this is the equation that we have. IO is equal to integral dc square dm plus 2h integral nc dm plus integral h square dm. Now, integral dc square dm is nothing but IC. We have defined it earlier, and that integral dc square dm is nothing but moment of inertia about the axis passing through center of mass. Plus, let's keep the middle term as it is. We'll address that middle term later. But the last term, integral h square dm, so h square can be taken outside, and we then have integral dm. Integral dm basically means we are adding these small masses that are present in the body, and what do we get is nothing but the total mass of the body. So we have IC plus 2h integral nc dm plus mh square. Integral dm gives us m. So we already have the terms that we need, which is IO is equal to IC plus mh square. But we have this extra term, and obviously that must be 0. This term must be 0. And why is that 0? Understanding that is very important. So let's understand why that term is 0. So let's have a look at the integral. Integral nc into dm. Integral nc into dm. So in this integral, what we are doing is basically, integration basically means summing up. It is the summation of product of all masses, with their distances from center of mass. Because this integral basically means that we are placing a dm mass over here, and then we are multiplying dm and nc, and we are doing this for all the masses all over the body. So basically what we are doing is we are summing up dm into dm1 into r1 plus dm2 into r2 plus dm3 into r3 and so on, where dm's are nothing but the small masses and ri's are nothing but the distances of dm from center of mass, and that is called as moment of mass. This product of mass and its distance from center of mass is called as moment of mass, and summation of moment of masses about center of mass is 0. Summation of moment of mass about center of mass is 0. Okay, so what we had is this term integral ncdm is equal to 0, and we had to prove that this integral ncdm is equal to 0. Now this integral ncdm is what I call moment of all, summation of moment of all masses about center of mass. And we know moment of mass is nothing but the product of mass multiplied by distance. So I've taken a basic example over here. I have two bodies, m and m. They are of same masses. Therefore, the center of mass will lie at the center between them. So the center of mass is at distance x from the left hand side mass, and also at a distance x from the right hand side mass. The coordinates of the center of mass are 0, 0. Now let's calculate the moment of these two masses about the center of mass. Okay, so moment, let's call this mass 1 and let's call this mass 2. So moment of mass 1 about center of mass, and that is equal to m into x. So we just take the mass and multiply with its distance from the center of mass. The moment of mass 2 about center of mass. Now over here it is m into minus x, because the second mass is the distance minus x from the center of mass, because it is on the left hand side. Now if we sum all the moment of masses, summation of moment of masses about center of mass, we get mx plus m into minus x. And we can clearly see that they both cancel out each other and we get the answer 0. And that is why I say that the summation of moment of all the masses about center of mass is equal to 0. And therefore this term, integral NCDM, has to be 0. So let's get back to the derivation. So finally, we have seen that why this middle term is 0, and I'll just write down the reason. The reason for this is integral NCDM is equal to 0 because summation of moment of all masses about center of mass is equal to 0. And when that term becomes 0, we finally have IO is equal to IC plus MH square. Okay, so let's solve this question now, with which we started the lecture. So as we have seen that I is equal to IC plus MH square. IC, as it is given to us, ML square by 12 plus M, and the distance between the two parallel axes is L by 2. So we have L by 2 ka square, and that is nothing but ML square by 12 plus ML square by 4. So I multiply by 3 in the numerator and denominator, the second fraction, and what I get is 3 plus 1 4 4 ML square by 12. 4 3s are 12, and this is the answer that we were looking for. So I dash in this place of question mark, I can now write down ml square by 3. So the moment of inertia of the rod about an axis through one end of the rod is nothing but ml square by 3. And we have calculated this using the parallel axis theorem. Thank you very much.